Any questions on those? You just, graphing them and evaluating the points and et cetera, finding domain, range, et cetera. We will be exploring these in greater detail later on in the textbook, but this is our first look at them. I like the way I prefer to do it, introduce them in a simpler setting and use them more complicated later on to kind of develop our skill with them as we move along. So everyone's okay with the problems in 3.4? Okay, I guess they're not too bad, so we're in good shape. Okay, so we move on now to taking inverse functions of those. That's 3.5 is the inverse functions of the exponentials, which are called logarithms. Inverse exponentials, also called the logarithms. Okay, remember how we found an inverse. Let's recall. Let's start with our function f of x as an exponential. Let's just start with 2 to the x. Remember, to find the inverse function, we did one simple thing. We set this equal to y. And to find the inverse, you're actually swapping the x and the y coordinates. Here's my x, there's my y. And look at the line y equal to x. Over here. And the inverse function is I swap the x and the y coordinates. So this becomes my x is equal to 2 to the y. That new function there is my inverse function. If I can solve for it, we can't solve for it, so we give it a name. But you can take a look at what this looks like. There's my 2 to the x, looks something like this. That goes to 0, 1. So the other one is kind of like symmetric with respect to that. It looks like this. That's going to be over here. That's 1, 0, and it's going to kind of go in that direction. Kind of a symmetry about that line. We call this inverse function, inverse log function, or inverse exponential function, excuse me, inverse exponential function. We call it a logarithmic function. And we give it a special notation. So here I can't explicitly solve for y. So this is the one form of a log function. This is a log in this form. But what we do is we create a name for it. We give it a name, and we call this would be called the log, I'll say y, so it's y, is equal to, we're going to give it a name, y is equal to the log, and we put a little subscript here, that means base 2, that's the base 2 of x. So these mean the same thing. This is the exponential form. And here's the exponential form. Exponential form. And this is nothing more than the logarithmic form, or log form. They mean the same thing. But very often, what we will do is when we're talking about logs, we will switch back to the exponential form to understand things a little bit better. Now, you will often hear the fact that people say, this is kind of what you hear, logarithms are exponents. You often hear that. Why is that? Well, look where the y is. The y is the log, and what is it? It's the exponent of the base. Now, you might have other, if you will, other sorts of logarithms. They all have the same general shape, just like the exponentials also have that same general shape. But you might have some others, so other logs. So here's some other examples. And so you might have your y equal to 3 to the x. Well, that's equivalent to the exponential form of x equal to 3 to the y, or the logarithmic form, the log in the base 3 of x is equal to y. The other day, we introduced our new base e, so you might have the other function, y equals to e to the x, or x equal to e to the y. What we do, you can write this way. This is the log in the base e of x is equal to y. Or what we do is we give this a special name. And we do ln. And that means the natural log. We don't have to write the base. This is implied that the base there is equal to that. So this is called the natural log. But that's the natural exponential function. Natural log function. And another common one we have is when the base is 10. That's our place value number system. The amount y is 10 to the x, and then again the exponential form of that is x is equal to 10 to the y. The logarithmic form looks like this. You typically might write log in the base 10 of x equal to that y, or what you will see instead of that is, instead of writing it that way, capital log, and that means log in the base 10 of x. This is given the name of a common logarithm. That's a common log. And what do? Well, they're inverse functions, so they do undo exponential functions. So that's their primary focus is the logarithm will undo an exponential function. What do I mean by that? Just like the square root function will undo a squaring function, a logarithm will undo a exponential function. We'll be doing more of these. I'm just going to show you. We'll be doing more of this in chapter 4 when we start working with functions a little bit more. But I'll just show you the primary purpose. For example, if you have a y is equal to, say, e to the x, and if I take logarithms of both sides, I take the natural log, because that's the natural base e, so I take the natural log of both sides, it will undo that and just give me the natural log of y. They cancel it out to give me x. So it's like you start with x in your domain, you compute e to the x, that gives me a y value. The logarithm takes you back to your input x. And the same thing if you had y equal to 2 to the x. Well, what could I do? I could take the log in the base 2 of that y, and the log in the base 2 of this expression would also just give me x. So they undo it, just like the square and the square root come in that sort of range. Now we also, found the inverse by swapping the two bases. I mean, the x and the y's. So this also leads to a way of determining the domain and ranges. Let me kind of show you this and illustrate. This is an easy way of remembering the domain and range of these new class of functions. Let's take a look at the domain and the range associated with these. You can kind of see from the picture I have up here, but let's look at it in a different way. Remember the exponential function. Let's start with the exponential function. Y equals to, say, 2 to the x. Well, we already know the domain for that. The domain is the set of all elements x, that x can be any real number. It doesn't matter. It's always a real number. The range for this, set of all elements y, such that y has to be strictly greater than 0. It's a real number, but it's strictly positive. Take a look at the picture over here. This is our picture. put any value in for x, but I will only get positive values out for my range. Never quite get to 0. It gets closer and closer to it, but it does. Now, this is an increasing exponential. If you happen to put a negative in front of that, it'll be a decreasing exponential. We'll talk about that more later on. But remember, this is the x and the y. So if I look at the logarithmic function, and this doesn't hold all the time for everything, but this holds over here for y equal to the, say the log in the base 2 of x. Well, how did we find that function? What did we do? Remember, we swapped the x and the y coordinates. So what happens here? The domain and the ranges also swap. So for here, the domain for the logarithm, I'll just swap them. The x and y change their roles, is now the set of all elements x such that x is a real number greater than 0. And the range is the set of all elements y such that y is any real number. So let's take a look at the graph of this. Remember, we're just going about the line y equal to x. So I can put my coordinates over here, my x and y, and my logarithmic function. The 0, comma 1 goes over here to 1, comma 0. It swaps over here, and it looks like that. Notice the domain. I can't put any number. I can't put anything. I can't put a 0 in for a logarithm. It's not defined. I can't put any negative value in for a logarithm. It's not defined. So my domain has to be strictly greater than 0. But look at the range. I can go all the way down here to minus infinity and all the way up here to plus infinity. So the y value can take on anything. There's my exponential, there's my logarithmic function. And you can see how I get it. I just swap the x and the y, or I could take this graph of that function and flip it about the line y equal to x. Because when I flip it about that line, my x-axis becomes my y-axis becomes my x-axis. And just flips it around. And that's what you get over here. You get the, kind of the mirror image across that line y equal to x. Now, in general, there might be some slight differences for functions later on, but in general, you can think of that when you look at this function and its inverse, you just swap the domain and ranges. Where doesn't it work? It does not work for those trig functions because it was no longer. Luckily over here, my inverse function has a full range. I don't have to restrict it. This is automatically, just by taking and flipping that, this is still a function. Whereas with inverse trig, I went from that axis for the function, if I looked at this way over here, but over here, to this axis for the inverse. That was not a function, so I had to restrict the thought here on this as we went from minus pi over 2 to pi over 2. So that's a little bit different. Okay, so let's see if we can evaluate some logarithms, and then we're going to look at something called a change of base. So let's do some logarithmic evaluations of the function. Logarithmic function evaluations. So let's say I have my f of x is the log in the base 2 of x, okay? And say I want to evaluate f at 2. So I want to compute the log in the base 2 of 2. How do I do that? Now, you're going to notice on your calculators, most of them don't have a log in the base 2 button. We're going to show you how to fudge that. But the way to look at these is not in its logarithmic form. What you want to do is rewrite it in terms of its exponential form. So you want to write the exponential form of the logarithm, meaning the logarithm is the exponent of our exponential function. And this is a way of being able to determine, without the use of the calculator, the value of that function. Let's take a look at it. So, for example, what is the logarithmic form of this? Remember, this is our y. So if I switch it around, the logarithmic form is x is equal to 2 to the y. And that's my logarithm over here. Okay. So if I come over here and replace x with 2, I want to find out what my y value is to make this a true statement. So this over here translates into 2 is equal to 2 to the y. So what does that tell me y must equal for this to be an equal statement over here? 1. I need the same exponent. That's 2 to the first. So this tells me, in this case, this has to equal the value 1. Easily do the exponential. That's one example. Let's take a look at a couple more examples with the same function over here. See if you can figure this one out. Tell me if I wanted to compute f at, in this case, 8. F at 8. See if you can figure that one out. So that's a log in the base 2 of the number 8. Try that for a second and see what you get. Use its exponential form. And hopefully you will get this number out. Does anybody want to see that? I want to see how I got 3 out of that. Okay, let's plug it in. So I'm using this formulation, and I'm replacing x with 8 is equal to 2 to the y. So I get 8 is equal to 2 to the y. So 2 to what power gives me 8? That's 3. 2 cubed is 8. Or I can rewrite 8 over here as 2 to the third power. 2 cubed is 8 is equal to 2 to the y. The y, the logarithms are the exponents. That's the exponent associated with that. You can kind of see how to compute some of these values fairly easily. Let's try this one. See if we can figure out this one. Let's try f at 1/2. You can figure out f at 1/2 and what sort of value you get for your logarithm, the y value. What does that equal? The same log in the base 2. -1. Does anyone want to see how I got that one? Yes, Liam, you have a question? Hand raised over here. No, okay, I wasn't sure. Making sure. Does anyone want to see how I got -1 for that? Okay, let's do the same strategy. Now I'm looking at this over here, and this is equivalent to my exponential form, which is my x value, okay, which is now 1/2, that's my x, is equal to 2 to the y. Well, let's rewrite this 1/2 using exponents, because that's what we're dealing with, exponents. 1/2 is really 2 to the negative first power by the rules for exponents. What is my y value? Well, the y value is nothing more than the exponent -1. It looks a little strange. It's a little bit strange to do that, but that's how you figure it. Use the exponential form, and then it makes sense to you. And we're going to develop, later on in the textbook, we're going to develop some laws for logarithms, and we'll have the rules for the exponentials. There's equivalent rules or laws for logarithms as there are for the rules and laws of exponents and exponentials. But we will do those at a later time. Okay. Now you can do the same thing for any other base. Let me try a different base over here and see if you can figure these out. So say, for example, I had the base of, let me put another example, new base, new example. So here's my f of x is equal to this. So let's say my y then is equal to the log in the base 3 of x. And I wanted to compute the following. Try these. So I want to compute the log in the base 3 of 27 and the log in the base 3 of 1/9. Try those two and see if you can figure out what the exact answer is. Now on a lot of calculators you won't see those log buttons. We're going to show how to handle it so you can. Does anyone want to see how I found 1 and 2? I'll kind of see how that approach is. If that's okay. Number 1, you just get 3, because why? I'm comparing 27 to 3 to what power? The what power is 3. 3 times 3 times 3 is 27. Comparing 1/9 to 3 to what power? Well, 1/9 is 3 to the -2, so my logarithm is -2. Okay, so if they fall on these nice values, they're easy to compute. But what about other values? For example, let's say I take that same one and I wanted to compute the following. Say the log in the base 3 of, say, 12. Well, if I set the exponential form up, it's a little bit harder. So I'm saying that 12 is equal to 3 to what power? That's the y value. What power is that? Well, I can't do it exactly, can I? I can put in 2. If I do y is equal to 2, so y equal to 2 will give me 9 over here. So I have 12. It doesn't equal 9, but that's what I would get. Now, if I did y equal to 3, okay, what would I get? I would get 12 equal to 27. So I know the number should, in many cases, be between 2 and 3. So what I could do is, it's an approximation. Let's keep trying to put it in. I want to put 3 to the, let's do 2.1 power. And I could go plug that into my calculator and see what I get. We're not going to be doing this, obviously, so 3 and raise it to the 2.1 power, you get 10.04. Okay, let's raise it to the 2. That's not quite close. Let's do the 2.2. So 3 raising it to the 2.2 power, I get 11.2. So this gives me approximately equal to 10. 3 to the 2.2 is approximately equal to 11. Let's do 2.3. So 3 raise it to the 2.3 power, and I get 12.5. So 3 to the 2.3 is approximately 12.5. So I know it's in between them. And I could keep doing this forever and ever. We don't want to do that. We'd like to find kind of the exact value for that. And that's what the calculators do. They give us all those in between. And if I wanted to kind of do that, I would get, let me just tell you what the actual answer is. My calculator, the actual, approximation is, to this answer is approximately equal to, and I'm going to show you how I got this, 2.2618595, etc. It's an irrational number, and it keeps going on. So meaning if I take my log in the base 3 of 12, that's the number I get. Or, meaning 3 to this power, I'll put it over here, so 3 to that power is equal to 12. And you can try that on your calculator, you see it does work. So how do I find logarithmic values for things that are not these nice, perfect exponents that we can do by inspection. Well, for that, we need a log button. So we have log buttons to do that. And those are calculated within your calculator. Now, on most calculators, you only have 2 log buttons. So most calculators only give you either the natural log or the common. So how is it that we find other logarithmic values? So on your calculator, you either have what we call the natural log function, and it's an ln function, or the common log function, which is log. Now what is that? That is the natural log in the base e. So that's the natural log of x, which is the log in the base e. This is, you know, a log in the base e, but it's written as that. This is the common log, log of x, which is the log in the base 10 of x. Common is base 10, natural is base e. We only have those 2 buttons. So how is it that we can find other logarithms? That comes about by doing something called a change of base. This is going to be a little trick to allow us, if you will, to compute any logarithm value using either one of those logarithmic values. We only need 1, but they put 2 on the calculator because there is some use for a common logarithm. This is kind of related to our number system, which is a base 10 number system. So let's take a look and find out how we kind of show what that is and prove that is. So let's say in general we have this. So we have my y is equal to the log in the base b of x. So b is any base, 2, 3, whatever base you want. Okay, we're going to start with that and see if we can in some way work with these other log buttons to be able to find values. Let's first start off by rewriting the exponential form of that. So remember, this is equivalent to b to the y is equal to x. That's the equivalent exponential form of that. The logarithms are the exponents to that base. Okay? We're going to use one of the properties of logarithms, of rules of logarithms that we have not developed yet. So this is a caveat. I'm going to prove this, but with something that you don't know just yet. It's the easiest way to do it at this level. We have a property of logs that if I do the following, so if I take the log in the base b of both sides of this, okay, I can bring everything down. This is the property. For example, I start with this. B to the y, is equal to x. What I can do is take either a natural log or a common log, any other logarithm. This is something that's not been proven yet. We will prove it later on in the text, but I'm going to use it here just so you can see where it comes from. It does come from someplace. I don't want to just show you the result. But let's try the natural log. Usually I use the natural log because y only has two letters as opposed to 3. So I'll take the natural log of this side. Okay. Here's the property. When you take the any log of some x base raised to a power, you're able to bring down the exponents. Now, some of you may remember this as a property, and we'll show you and prove it later on, but we need some more stuff to do that with. So I can rewrite this now as y times the natural log of b to the y, times the natural log of b is equal to the natural log of x. Now, what am I trying to find out here? I want to solve for y. So I can simply, in this case, I can simply divide both sides by the natural log of b. By dividing that by the natural log of b, I get my y value. So I get y over here is equal to the natural log of x over the natural log of b. But what is y? Y is the log in the base b of x is equal to the natural log of x over the natural log of b. That is what we call our change of base formula. It allows me to change from base b over to base e. Then I can put that into my calculator and find the value for any x. If I want the log in the base 2, or like in this case, the previous case, I wanted the log in the base 3 of 12. What do? I just do the natural log of 12 over the natural log of 3, the base, plug that in, and that's where I got that 2.3, whatever, 2.26, whatever it was. I could also have taken the common log. So the other way of writing this is my log in the base b of x can be written as the common log of x over the common log, or log in the base 10 of b. So both of these are called my change of base formulas. And this is a very simple demonstration. I didn't formally prove it because I have to prove that particular property, and I haven't done that. But we will later on. So this will enable us to graph any log on, if you will, our calculators. Let's take a calculator. Say, for example, somebody wants you to graph the log in the base 2 of something on a calculator. How should you do that? So look at graphing now. Let's say someone says, graph this. Log of the base 2 of x. Okay. I don't have a log of the base 2 on my calculator. So what would I do? Well, I'd simply come over to here. Let me show you my TI calculator and how I turn around and graph that. So let's turn this on. Get this out. And now I want to graph that. Well, I don't have that button, so what do? You can either use the LOG button here or the LN. I usually like to use the LN. So I'll do LN of x. And I'm changing the base from the base 2 to the natural base. And then divide that by the natural log of the base that I'm changing from, which is base 2. So that's done, and if I want to, I can simply graph that result, and there it is. Now you have to be careful with these logarithms. If you look over here, it looks like it stops at that point. It looks like you go down 1, 2, 3 units, it stops. It doesn't. That's an artifact of the numerical rounding errors in here. It keeps going all the way down to infinity. So it gets closer and closer to that y-axis and goes to infinity. And it's a little bit harder to do. Now you can also do the same thing using Desmos. Now in here, this is where you kind of look at, say, y is equal to. This tends to be a little bit easier. We can look for the logarithmic functions. You see, I'm using too much over here. So let's look for the, okay. So in this one, you can actually graph a log in any base. So this is what's nice about Desmos. You don't have to use that change of base. So I could graph the same thing over here, and it's asking me to do base 2, and I'll do with x. So there it is. And let's just validate that it's the same thing I have for the other case over here. So let's say I want to do, y equals the ln of x divided by ln of 2. And notice it falls exactly on top of the other graph. I could turn that off or turn that on. And notice how on this graphing device, it doesn't cut off. Whereas in the other one, at 3, you just couldn't see the drawing anymore. But here, if you go down and zoom in, it is still blue and or red all the way down the y-axis. So it kind of shows you, that aspect of it. So be careful when you're dealing with logs as you get close to the y-axis, meaning as you get closer and closer to your input, your domain value being 0. 0 is not in a domain, but if you get closer to that value of 0, you get closer and closer to minus infinity. It just doesn't stop like it does on this graph over here. This one, it looks like it just kind of stops over here and doesn't continue down. So I just want to kind of make you notice that. Okay. So that's pretty much everything we want. Now, for example, if somebody said you wanted to compute now, how to graph, it can also evaluate functions. So if someone says, I want you to evaluate the log in the base 3. Well, let's do this one. A more common example would be a natural log. Let's take a common, more natural example, no pun intended. Let's say a natural log of 5. Well, here we just use our, if you will, our calculator. And plug it in over there, and you get something very easy. I'm going to put that calculator, there it is. ln of 5. So nothing fancy to do there. That is just equal to approximately 1.609. So, but what if instead I wanted to do the log in the base 2 of 5? The way to do that is to use either common logarithms or natural logarithms. I prefer the natural because it's only 2 letters to write down. So that would be the natural log of 5, which we already computed, over the natural log of 2. I take that and divide that by the natural log of 2, and I would get the answer, which is approximately equal to 2.322, approximately. It's rounded to the nearest thousandth. And look at that. Does it make sense? So I'm saying 5 is equal to 2 to what power? Well, it's approximately 2.322. So if I take 2 and raise it to the 2.322 power, I get something a little bit larger than 5, but reasonably close. This gives me 5.00025 approximately. You can see, not bad. But that's how you do those evaluations on your calculator. Now, base 2 is very important in computer science. So those of you that are involved with computer science, you will be doing calculations in base 2. So just so you know, that's a binary system. 2 is also related to that. So that's an important base. But you can see with the Desmos, it's not an issue because you can put in any base. Now, some other calculators allow you to put in the bases. In this calculator too, you can actually do that. If you want to do it, you can search for it. You don't have to do it, but I think it's easy to do it the other way. But let me just show you where you can actually do that separately. I don't do it too often, that's why I may have to search for it for a second. But over here, we can look at, I think it's under the math key over here, and I think it's under number, if I'm not mistaken. Maybe not. Keep going down. I know somewhere here. It's not complex. Not probability. Not the fractions. Maybe it is on the math, or there's some more. It probably is on the math over here. I don't use it too often. Here we go. Log base. There we go. So you can actually do it that way with this calculator. It's under the math function, very similar to Desmos. So you do log in the base 2 of that value that I just did, 5. Plug it in, and I will get that 2.3219. I approximated that to 2.322. Okay, so it's there as well too. So we have both of those as options. Okay, so that's all we need for this section at 3.5, logarithms. For now, we're going to develop a lot more properties. Can you graph them? Can you evaluate them? Can you do that change of base? That's about it. Nothing too complicated. Okay, that's the end of all the functions, their base functions, I should say, we will be using in this course. So, moving forward, to model phenomena in the world, or in your science or engineering classes, we use a series of different types of functions. And the types of functions, just as a summary over here that we use, are the algebraic functions that we covered, and the transcendental functions that we covered. So the types of functions we're looking at throughout the rest of the course, they're going to come in two different varieties. The first class of functions are the algebraic. And what do we introduce? Well, we introduce polynomials. We introduce radicals. We also have a little bit about absolute value function, as well as our rational functions. So those are the four subclasses of functions we're going to be working with in this course. But then we also have transcendental. And we introduce the trig functions, mainly sine, cosine, and tangent, and then they're inverse functions. So the inverse trig functions. We also introduce the exponential functions. We'll be working with those, as well as their inverse functions, which are called the logarithmic functions. So those throughout this course and throughout calculus